A special talks this summer. Usually we don't run our speaker series during the summer, but because we have this opportunity, we activated the event for this Tuesday. I'm very pleased to have with us Hedda Schmidtke. Hedda is actually one of the first faculty members in the new campus in Rwanda. The way it works is she has her home base here in Silicon Valley and has spent this last year part-time in Pittsburgh, part-time here, connecting with us and starting some activities. And she'll talk about her interests in context-aware computing, an area that I share with her, before she heads off to Rwanda, where we hope we'll keep some connection going. So with that, Hedda.
Thank you for the introduction. Do we have an echo here? Yeah, with the first commercial context awareness platform being published by Qualcomm recently, the question starts to become more important as to whether context-aware systems with reasoning abilities can be scalable. The systems that we have at the moment are running very well in the labs in the range of 100 people. But the question is, when we go to 1 million people, will this scale up? So I'd like to take this opportunity to discuss with you about this. So in this discussion, I want to have a look at both perspectives. First, I will talk a bit about why we have good reasons to believe that reasoning about context is indeed hard. I will go into results from spatial and temporal calculi from the area of constraint satisfaction problems, and also have a brief look at spatial and temporal modal logics there, and the negative results we have from these areas. But also there are some results that can make us hopeful. There are experimental results from context-aware systems running very well in the labs, and also from the area of spatial and temporal calculi, we can find many fragments of calculi that are tractable. So then the question is, do experimental results and theory disagree? Why does it look like that? And what kind of systems are running in context-aware computing? And then we can answer the questions whether these systems scale. The aims of the talks of this talk are to look at a well-behaved class of contextual reasoning systems which are based on a partial order relation system and which scale very well, which are expressive, and I will also show three applications that we have implemented. So the statement will be, context-aware systems are both smart and scalable. The outline of the talk follows this structure. I will start with a little bit about my background, how I came to think about context. Then I will elaborate on reasoning about context from the perspective of why it is computationally hard, and then outline the other perspective. And in the second part of the talk, I'll look at context awareness from 4 points of views, 4 theoretical points of views, which can be found in existing systems, and I will then briefly show some implementations we did. Yeah, let me say a little bit about my background. I did my master thesis on relative localization of extended objects, and while I was doing that, I realized that the notion of extension is a context-dependent one. It doesn't make sense to talk about an extended object if we don't know in which context. So a country like Switzerland is certainly extended as long as I'm a pedestrian, but if I look at the whole world, it's not more than a dot in comparison to, let's say, Russia. During my PhD, I looked closer at such size constraints, and yeah, in my thesis is a characterization of spatial granularity with applications in knowledge representation and reasoning, but also geographic information systems, natural language processing, and even computer graphics. With this theoretical framework, I went to a conference, Context 2005, organized by Anne Day and Patrick Brésillion. And I was amazed at how important context is becoming in this new area of ubiquitous computing, which was very fascinating for me. And so when I met Professor Untitled at this context conference, and he told me he was looking for a knowledge representation person to put a reasoning framework under his context model, I decided to go to South Korea and try to do this. What came out of it at a workshop at Context 2007 was a context-oriented logical language for reasoning about context. And so Context is a biannual conference, so 2007 was the next one. There was none in 2009, but instead we went to Pervasive to present our formal verification method, which was based on the ontology framework that we had proposed before. In 2010, I went back to Germany, following an invitation by Michael Beigel, who then went to KIT to take over the TECO research group, where I became research director. I had several main projects, 20 papers, 2 of which got 3 awards. But also I realized in 2010 there was again no call for Context 2011. So I got a little bit of backup and wrote to the steering committee where the conference would be held. And if there was no place decided, whether we can do it in Karlsruhe. So we resurrected a Context 2011 in Karlsruhe, which I'm very happy about. And since an uneven year is upcoming, I'd like to take the chance to advertise Context 2013, which will be held in Trondheim in Norway. So if you haven't seen this wonderful place, that's a great chance. This is a very interdisciplinary conference with people from ubiquitous computing, talking to language processing people, and AI people. I think this is a very unique group, and I'd invite everybody interested in context to contribute and discuss there. So what did I do content-wise? I studied more of the systems side of it, looking into lightweight distributed intelligent sensing systems. Coming from a knowledge representation background, these are still knowledge-based systems, but right above the swarm level intelligence, so that these actually can scale up. That's That was the aim. Yeah, since 2012, I'm now with CMU Rwanda and a second affiliation here at Silicon Valley. Now, why is reasoning about context computationally hard? First of all, what is context? If we know that, we can know better what we're dealing with. Let me cite the framework of Lieberman and Selker. Traditional computing comes from a black box perspective. We have explicit input and output, and everything else is hidden. Context awareness adds implicit input. So everything that's not explicit input and output can be considered context. Especially we want to reason about things that come from sensors, but also state information, history information, things that we can learn from the way a user interacts with the system. A very famous characterization, I think the most cited, comes from Anand Day. He says context is any information that can be used to characterize the situation of an entity. And now comes the crucial part: an entity is a person, place, or object relevant to the interaction between user and application, including users and applications themselves. So this is a pretty interesting list of things. But can we make this more explicit? Sei Zhang and Runtae Gu put up this so-called 5W1H model, starting from a basic question that we can ask about an interaction with the user. We can derive 6 dimensions of entities that we can ask about. So this question is: who interacts when and where, with what, for what reason, and how? Who, again, is the persons, user groups, for instance, but also social relations in a social network, for instance, are things we want to reason about. User interests. And then when is the time of the interaction. We can have this easily from a timestamp, but also we want to think about things like time of day or meaningful times like vacation or holiday, birthday, things like that. The where dimension is has been studied most in all the location aware systems. We reason about location information that we get from GPS with geolocation services and so on. And coming back to Lieberman and Selker's definition of context-aware systems, we also want to think about histories and goals of the users, of the interaction of the system. That would be the Y dimension. And we want to reason about states, the active processes, both of the application and of the user. This is another domain. So let's look at space and time. Space and time have been studied since the 50s, starting with modal logic approaches. Arthur Pryor is credited most for starting the context dimension with his tense logic and his investigations on the indexical now, which later led to the hybrid logics put forward by proponents like Patrick Blackburn. We know that hybrid logics are p-space complete. The spatial logic put forward by Bennett, which gave us the first idea of the complexity of the RCC8 calculus is also in a fragment NP hard. So lots of negative results on that side. And if we go to more expressive formalisms like first order logic, here we have states, events, and temporal intervals in Allen's original paper. And we have the event calculus and situation calculus as important and widely used approaches, which are, since they are first order logic, semi-decidable. So not very good on that side. Now let's look at constraint satisfaction. Constraint satisfaction problems consist of a set of variables. Let's say, for instance, appointments in a calendar, a domain of values, for instance, time slots, and a set of constraints. Like, for instance, this appointment has to be before that appointment, or shouldn't be in parallel to this appointment, and so on. Constraint propagation is a category of algorithms that can be used to eliminate alternatives and find out a feasible schedule, or whether there is, for instance, a schedule at all. Of course, all this also applies to the spatial domain, where we are interested in layouts. There has been considerable research in that area in artificial intelligence, starting with Allen's interval calculus, which contains mereological relations. Intervals can be contained in other intervals. This is the Turing relation. There are directional relations like before and after, the direction of the time domain. And then there are topological relations like overlap. In Allen's calculus, those are directed. That means we distinguish between overlapping intervals that start earlier or those that end later. And then there is the point algebra. That was the one we discussed before, where we have certain time points, and we are just looking at point events without extension. And then there are spatial calculi, the region connection calculus, RCC8, I already mentioned, but also the cardinal direction calculus about directions north of, south of, west of, northwest of. All in all, we have 9 relations there. So here we get mostly negative results from the early publications. We have RCC8 turning out to be NP hard, likewise the interval algebra. But more positive, the point algebra is tractable, as is the cardinal direction calculus. On the negative side, we find that certain classes of RCC8 problems are well behaved, but if we, likewise interval algebra, but if we combine the two, some of our optimizations again break down. So the combinations seem to become harder too. All this doesn't look very good for running this on a mobile phone. So context awareness seems to be in trouble. But on the other hand, we have those maximal tractable subsets and optimization. And also we have results, for instance, that size constraints, putting size constraints into RCC8, into this algebra of regions and region connections, is for free. It doesn't make our problem harder. So all this a little bit mixed. Now, can there be a different perspective that reasoning about context can be fast? So let's look at the positive results. Already mentioned that RCC8 has subclasses which are tractable. And actually, if we look at the CSP problems, then we find that most problems, if we do randomized inputs, and we find that most problems are actually in one of those tractable subsets. So that's a positive result. Likewise for the interval algebra. And the cardinal direction calculus and the point algebra all are tractable. So that's also a very positive result. All in all, we know from this that the probability to run into a hard problem is very low. But now, again, we look at what happens when we scale up things. So it might be that in the lab, we have a very low probability, let's say 1 to 2,000, of running into an NP-hard problem. But now we go out into the real world. We have 1 million customers using it. Now the question is, if this is 1 per mil, we will run into lots of problems. So customers might end up being unhappy about the performance of the system, or even worse, we might get into something like a denial of service situation just by being overloaded with complex queries. So can we be can we try to remain in this class here? Okay, let's have a look at reasoning and context-aware systems. What do actual systems that we have running in the labs use? They use graph structures. We need something like computation about sensor values. And then they use a combination of ontologies, ontology languages, consisting of first-order logic for talking about space, time, sensor values, and also some traditional ontology languages, such as OWL, for talking about classes. What about those systems? Are those in danger of running into hard problems? Everything looks fine so far, but let's have a closer look. So what can we represent in graph structures? Especially in directed acyclic graph structures, hierarchies, like location hierarchies, user group hierarchies, but also we can represent time intervals in such hierarchies. We can also represent in a directed acyclic graph temporal order, space I already said, and also taxonomies, subclass relations can be represented in such a graph structure. So all this can be done in the kind of systems that we find in today's location-aware reasoning systems, those that use some form of reasoning. So now we can also argue that maybe reasoning isn't the most important part of context-aware system. To illustrate this a little bit, I've drawn a graph from that is a part of the whole context model of an application. And you can see this is a quite huge directed acyclic graph, and this is just a tiny portion of it. What this system does is it gets sensor input down here, illustrated, and down there, and then it passes this up through the graph, and those here, those round rectangles represent nodes that have a code snippet attached to it that is executed when the sensor activation reaches the node. So in comparison to what's done here, something like, for instance, open a file, this graph is a considerable portion. So I'd like to have a closer look at this. We also looked at how we can. Is this turned on? Can you hear me?
Yeah.
Okay.
Yeah,
This is an example of such a context-aware system. Consists of it's the most simple, the hello world of context awareness, the heater example, consisting of a sensor which senses the temperature in a room and an actuator which adjusts whether whether there should be heating this round or not. The sensor sends the value it senses through the context model, and for instance 13 degrees Celsius, this is checked against the threshold, and then we determine, okay, this is too cold, and this code snippet would be activated in order to avoid that we have an uncomfortable situation. And of course, this can be, additional information can come in, because we want usually something like personalized thresholds to be used here. So let's have a closer look at such directed acyclic graph structures, which are widely used in a range of systems. Directed acyclic graphs are trees are special kinds of directed acyclic graphs, but DAGs mostly have the same properties as trees. So they are directed. That is, we can't run into cycles. Nodes have distinct child and parent node. And in general, all graph search techniques that we can apply to trees, we can also apply to DAGs. Since trees are very well-behaved data structures, DAGs are also very well-behaved. The only thing we have to do is, because in a DAG, a node can have several parents, we have to make sure that we search a node just once. Usually we do this by marking the nodes, but as you can see, marking a node is not really something that increases space or time consumption considerably. So what can we represent? Let's look at expressiveness. We can represent partial orders over a domain. We can represent linear orders. And I wrote with uncertainty because sometimes we have just uncertain information about the size, for instance, of this room. I might guess that it is larger than 10 meters, but maybe I don't want to commit to it. So I say, okay, it's certainly larger than a meter, and it's certainly smaller than a kilometer. And then you can see I can have linear constraints with uncertainty also represented in a DAG. And another thing, if we add for any two nodes the join and meet of the two nodes, that is least upper bound and the greatest lower bound, then I get a lattice structure. And this can also be represented in a DAG. Let's have a closer look at pre-orders, partial orders, and lattice structures. I will present all the whole first order axiomatization for these, but this is all completely standard. This is just transitivity, reflexivity, so all the standard stuff that we know about orders, pre-orders, partial orders. What I'd like you to look at is the structure of these formula, of this axiomatization. So we have the universal quantifier here, and then we have a conjunctive part in front of here. Then we have our implication arrow. Sometimes we don't have an implication arrow, like here. And then we have, back here, we have a disjunctive part. And as you can see, there there is no disjunction, so we just have a single literal here. If we have a formula like this, then this is just the same, but the first part of this is empty. So you can see this has two conjuncts and one disjunct here. This has just one disjunct. Here we have again one disjunct. This is the partial order. Again, it's transitivity, having two conjuncts, one disjunct. And then we also have anti-symmetry for partial orders, which also consists just of two conjuncts, one disjunct. Now another result. We can, for every preorder, define an equivalence relation so that the preorder works like a partial order. Now let's look at this again. So we have this definition here. So wherever this comes up, we need to fill in those conjuncts here. So we have those conjuncts in here and in here. Conjuncts back here are okay. We don't worry about those. So again, just one disjunctive part in here. One disjunctive part, again, one disjunctive part, one disjunctive part. And so far, we never had more than one disjunctive part back here, meaning that we're only dealing with so-called horn clauses, which are particularly well behaved. This result states that all preorders have subrelations, which are also preorders. So if I start if you look again at our directed acyclic graph and you pick out one node and look at all the nodes below this node, you get another directed acyclic graph, right? And our directed acyclic graphs correspond to preorders, meaning we can do the same. And this is an interesting result with regard to expressiveness, because it means that any language that supports representing one preorder is powerful enough to represent an arbitrary number of preorders. We just have to introduce such entities and can have everything in one tree. So for instance, you have one directed acyclic graph in which you can put time, space, users, whatever. If you want 10 relations, it's not more complex than just having two. So this is an interesting result for expressiveness. And we can also define linear extensions for any preorder. And linear extension has is just a sub relation. But it has a couple of, it has especially one particular property. And this you can see here. This is the linearity constraint. So if I have two objects, I can order them in one of two ways. So either A is before B or B is before A. On the timeline, there is no other way, or they are at the same point, of course. There is no other way but those three possibilities, or two, for this smaller or at the same point. And this is a disjunction here. So this particular axiom is the only one that's not in the horn fragment. Now, how do we get from there to our lattice structures? We just introduce, we demand that there is a least upper bound and greatest lower bound, and then we can use these operations, join and meet, and increase the number of elements, of course, increases in the graph then. So this gets us more complex. But we don't leave the directed acyclic graph, the principal structure that we have been talking about. So now let's look at the constrained propagation perspective again. What we found out was from our discussions of preorders was that having more than one preorder did not change the logical framework. So we can have as many as we want if we have one. And we have observations like this from our earlier discussion. Ligozat's cardinal direction calculus with 2 linear orders with tractable. The point algebra is tractable, and size comparison comes for free, can be added, and is tractable. So as you can see, this is a very well-behaved round framework that we find also in constraint satisfaction. And there are theoretical results that support this. In particular, these are all contained in the so-called Ord-Horn class, which is a superclass of what we can have here, and a well-known tractable class, a subclass of the interval algebra. Only the linearity constraint is problematic. How do we do that? Usually, we just disregard it. We can, if we have, for instance, a partial order reasoner, it will just operate with partial orders all the time, and in the end do one linearization, which is then arbitrary in the order of the portions of the graph which are in parallel. If we wanted to reflect this in our reasoning system, this would lead to an explosion of uncertainty, which doesn't give us any benefit. So how far can we get with this framework? Here is a list of relations that I have mentioned before. So part of all the mereological relations are preorders. Then we have a size constraint smaller than. If a region A is part of a region B, the region A is also smaller than region B. We have cardinal directions. We have during or equal as a mereological relation, a part of relation in time. With a shorter duration than interval that contains another interval is of course longer as a linear extension. Then we have before or the same time over time points as another preorder. And we have the subclass relation is a preorder with cardinality constraints as its linear extension. So if you remember the 6 dimensions, we have covered quite a few of them here with this simple framework. What did we do with this? First of all, we wanted an ontology language. I said before, we had OWL, first order logics, and graphs in a combination. And we wanted to have one framework that unifies all this. And accordingly, we designed a model language for reasoning about context. Idea is we have these kind of graphs representing these kind of region overlaps. And we had these design criteria. We wanted both a means for verification of context-aware applications, but also a decidable ontology language that can be used by applications. We wanted to have disjunctive formula in this. OWL doesn't support us. on that part to represent alternatives and uncertainty. And we wanted to talk about sensor values, of course. So how does this language look like? We have context variables, our basic names for contexts, like room 129A or a certain meeting. And a meeting, of course, has a space and a time. We can use these constructions to access the different dimensions of a context. We can have a join of regions, for instance. This room, of course, is just a spatial object. It probably doesn't have a temporal dimension, but a meeting has both a space and a time and people. And yeah, we also wanted to have such formula. And up to here, with basic this basic preorder structures, and up to here, we're in the very well-behaved framework. When we then add our meta reasoning, we leave this framework of graphs, and it becomes more complex, but it's still decidable. So we can then verify such context-triggered programs. But I want to quickly have a short look at our implementations. This was a project to go beyond simple activity recognition. We had a well-working activity recognizer, and so it can distinguish walking, talking, holding the phone, and some other activities. We also added in location information and time information. And with this framework, the user could create certain, a meeting, for instance, to be held at a certain point, a spatial point or spatial region, at a certain recurrent time. Also, we had people represented by their voice patterns, so we could create such compound contexts and recognize them. Another system used the context awareness framework for a content recommendation. Here we had basically this is a cooperation with Microsoft Research Asia. So here we had this kind of tag clouds. Inside, these are structured with the kind of graphs that we discussed about, and then we can retrieve content that has a similar structure than our current context. So we have an interest, time, and space in this application as the context dimensions. We also put this onto sensor nodes to look at what else we can do with this simple directed acyclic graphs. This application constructs a dynamically constructs a directed acyclic graph by a measurement. So we have some seismic activity. Somebody is knocking here in the center of the table, and seismic activity has a smooth gradient. That means if I knock here, then, or if the earthquake is here, this is a small earthquake, of course, then this node has the highest registers, the highest vibration, these ones a little bit lower, and so on. So we have certain measurement values. And from the comparison of measurement values, the larger or equal relation is a directed acyclic, Spencer-directed acyclic graph, starting from with this node as a root node, and we can pass messages from here to here just by identifying nodes with their, instead of an ID, with their measured sensor value. In this way, I can send messages towards the center of the earthquake or away from it. And yeah, this is with a, there is no centralized graph structure or something that's built dynamically between the nodes. And yeah, this works for any measurable quantity that has such a smooth gradient. Okay, in summary, we've discussed 3 mechanisms for tractable reasoning about context and found the common core of all of them to be pre-orders. We looked at directed acyclic graphs, a modal logic framework, and constraint propagation approaches that are very powerful. And yeah, I'd like to conclude that context-aware systems that are based on such pre-orders are both smart and scalable. Thank you.
Yeah, could you toss me that red? Anyway, I want to start by this fantastic talk. I really enjoyed your walk through all of this theoretical basis for context, and I just really haven't seen people go into that depth and treat it this way. And I guess I just wonder who are the other people? You know, a lot of people doing context-aware systems, and just how do you feel about their theoretical underpinnings? Are there some that have done a good job?
There are, in the formal verification area for context-aware systems, we have some approaches using ambient calculus or bigraphs. One of the shortcomings of ambient calculus is that it just discusses tree structures, where we go one step further and generalize this a little bit towards the directed acyclic graphs.
When you showed your mobile app, it reminded me of Joy's life logger work. I was just interested if you've had a chance to look at what he's done and compared it to what you've done.
I've looked at a few life logger applications, yeah, and this is clearly what we had in mind. Life logging was one of the applications, but also we wanted to trigger certain applications in certain contexts. So not only logging, but also, yeah, proactive actions, right.
I noticed some of the things that you measured was walking, talking, or holding. I was just curious how you use that type of information.
Yeah, for instance, if you want to know who the user is talking to on the phone, you can do that if you have the voice patterns. So we have a voice recognition system. I haven't shown that work. We have activity recognition. I mean, you can trigger certain applications you shouldn't trigger while the user is walking, but you can do that when it's just calm or something.
So it seems that you used multiple sensors on the phone, not including the audio input and some of the sensors as well.
Space, time, and in this case, activity. Yeah. And for the other application, we also had voice, so the microphone too. We used as much as possible. But I think there will.
Is there room, perhaps, requirement for a process to kill off another process? If you want to see if either of two things is true, and you discover that one is, you might want to kill the alternate question, the computation that goes into the alternate question.
Yeah, in this.
It makes some problems terminate that would otherwise not.
So if you look at this kind of graph structures that we have here, this kind of typical graph structure. So what we are doing is classifying the current context according to several domains of context. So in this simple application, we just we can do this with message passing, and then we can trigger certain code snippets that do something meaningful, like open a file or starting the presentation application or something. So as soon as one of them is reached, they are started, and this can, of course, lead to some concurrency problems in this graph. So we should make sure that one context has been handled before the next one comes in. But this is a problem we didn't
You were saying
address.
only classify the context. Do you do sensor fusion or context fusion? You know, weighting, combining, something like that, or averaging. In your other example, you might like to know temperature average.
Yeah, what we are doing is we have this is just a knowledge-based part of it. So there is a whole machine learning parts also underneath it, where we classify things using standard machine learning techniques. For instance, we have this walking and talking example here. For instance, this is generated by a fuzzy inference system, and then it comes into this graph structure, and we can combine this in a semantic way on top of it. But we're also working on how we can get the two together. But I mean, this is one of the great challenges of learning research. Right?
So
How to get the two.
did you get a chance to talk to Seneca, one of my students here? Because he built an ad hoc graph structure where the nodes were actually combining nodes rather than reasoning nodes. So that is, stuff would propagate up, but averaging or decisions being made at each node before propagating further. So it's I wouldn't say it's a directed, it's not a formalist DAG, but it's an informal DAG, if you like.
I'd like to talk to him, yeah.
Yeah, I have a few questions. I'll start with the last one. I'm wondering to what degree it would be easy to invert this. So if you know the kind of conclusion you want to draw, then can I determine the kinds of, say, sensors or measurements or values in the environment that I would need to reliably measure to draw that conclusion?
The framework I showed is just for deductive reasoning, but of course you can use an abductive reasoner with that too. I mean, this is just the straightforward way is just, and especially if you have just this, I mean, abduction is computationally harder than this kind of subclassing that we just used here, which is basically, I mean, you're not really branching out there, you don't do any backtracking, you're just doing this typical horn formula mechanism. So that's all very well behaved. We're in a class here what we can really run in real time on a mobile phone or on our sensor network. That was the idea. But of course, abduction is hugely important and very exciting area. Yeah.
My second question was, I wonder if you could talk a little bit about how this computational scale, so as the real-world situations you're trying to model or take account of, have a lot more data, a lot more length of relationships and so on, how the computation efficiency or inefficiency would scale.
I mean, if we think about a concrete example like this subclassing point where we go through this graph and then trigger some concrete action, and also if you look at this kind of operation, then you're certainly in a very well-behaved class of queries to a tree structure, right? We're just interested in the path of to the root node for that case. And if you look at the internet, it consists of tree structures, and it does scale very well. I mean, trees have very good properties with respect to scalability, right? But it depends on the queries you're asking. If you're asking a very complex query with disjunctions in it, then of course you have to do this backtracking, right? Every time your disjunction hits some some problem, then you need to backtrack and pick the next one, right? So this gets you more complexity. Mm-hmm.
This approach of going with the logical AI approach, it's a very exciting idea because it's computationally understood. And what I'm worried about, of course, is the uncertainty, which is always part of any contextual environment. And I notice you touch on that with your fuzzy learning thing. And is there anything else you want to say about uncertainty in contextual reasoning and user experiences?
Yeah, currently, so this is a fuzzy inference system, and the good thing about a fuzzy inference system is that it produces certainty values for each classification. So I might think that this is talking with a certainty of 60% and walking maybe has 40%, then I'm not really sure. And it could be both, actually. I can talk and walk at the same time. Using such uncertainty information can, of course, be particularly interesting to an application. But of course, the logic that we use also needs to be a kind of logic that can do something with it. A logic that can do this is, for instance, possibilistic logics, and we've been working on a possibilistic extension of that basic reasoning mechanism where we have uncertainty annotations on the edges of the graph, and again, we have to be careful because possibilistic logics increase expressiveness, and with increased expressiveness, we have a chance to run again against the boundary of the trade-off, which we so nicely avoided here.
But you could certainly attach fuzzy rules to that and say, if it's walking X% and talking a certain percent, I'll trigger this action. So you could attach those actually at the action points, not all over the graph. It's really my set of rules. What do you do for me in these recognized circumstances?
Yes, I mean, I can start context awareness right on this level, right? So I have an activity which I recognize and I trigger an action. That's actually a very simple graph you have done, right? So you don't need much reasoning for that. But we have systems which use this reasoning ability in a very powerful way, and this gives us smartness beyond simple action and response systems.
I know I'm starting to notice people leaving, so I can't help but ask one last question, and then I think we have to be outside, and that is a marketing question. For people to use your system, is there a place for them to go get it, or is there some way that you'd like colleagues to get in touch with you as part of that?
Yeah, you can certainly contact me by email. I'm
Hedda at
Hedda.
HEDDA at sv.cmu.edu.
Hedda at Andrew or Hedda.Schmidtke at sv.cmu.
Well, everyone join us outside for some cookies and sodas. Thank you so much.
Thank you very much.
Let's move out there instead of having people meet you here. That's what we like to do. So I'll turn off the recording. Excellent talk.